Okay, so we've been talking about ordinary differential equations in the past week. I wanted to give a couple of highlights to remind you of what that is on these short videos. So the first thing we start off with is for a linear first order differential equation, we can just write down what the solution is. So let's see how that goes. Linear, so this equation is looking for y as a function of x. So it's linear in y. We know the derivative operator is linear, so this is a linear operation. Multiplication of y by a scalar is a linear operation. And in fact, this scalar can be a function of x. It could be a quite complicated function of x. That's still allowed under linearity because it's still linear in y, even if it's nonlinear polynomial in x, equals a right-hand side, which is a function of x alone. There's no y over here. So let's review. This is linear. It's first order because there's only one derivative, not a second derivative. And it's an ordinary differential equation because there's only derivatives with respect to one thing. Okay, so here's the solution. Well, it's a little bit complicated. So y is e to the exponent of this p of x with a minus sign. So you need to integrate that, get a minus sign there. Then it's that factor is multiplied by q of x, the right-hand side, raised to e to the power, another integral of this p of x, this time with a positive sign. That whole thing multiplied together gets integrated with x, plus another part that's just a constant that we have to determine based on the initial conditions, that goes like e to the minus integral of p of x dx. All right, great. Let's think about a few things we could do to simplify this original equation that would make the solution a little bit easier. Well, maybe the easiest thing to do is to consider what happens if we set q of x to 0. Then this whole first term drops out and we only get the second one. Q of x equals 0 is a special kind of equation where it's called homogeneous, and that's because it has every term depends on y in the following way. They're all the same in respect to y, and then if you set y equal to 0, they would actually solve this equation. dy dx, if y is equal to 0 is 0, p of x times y, if y is equal to 0 is 0, and if q of x is equal to 0, then it's a homogeneous first order linear differential equation. In the homogeneous case, we don't get this whole complicated first term, we only get the second one. Excellent. We can make things even simpler for ourselves. If we set p of x, rather than having it be a function of x, we make it constant coefficient. So just a constant there. In that case, this derivative, or this integral in the exponent becomes trivial. And so a linear first order differential equation, ordinary differential equation with constant coefficients and homogeneous, has only the second part, and that integral becomes trivial when p of x is constant, which is it's whatever the constant is times x. So you can see that from that, we get our guess and check solution that we are often using in class from that kind of system. So if that's the homogeneous system, what's this other crazy thing called? Well, this is called the particular solution. And it's the part that cancels out the q of x when evaluating the right-hand side. So if q of x is non-zero, you need this whole thing to cancel it out. And notice that it doesn't have any stray parameters in it. It doesn't have any constants in it. The only constant that needs to be evaluated with the initial conditions comes on the homogeneous part of the solution.